Good day, lecturer and classmates. We'll be presenting topic 3, Mechanical Properties of Materials for FMB20303 Strength of Materials. We'll see how materials stretch, squash, and sometimes break, and what those curves and symbols actually mean. Key intent. Set context for tests, tension, compression, stress-strain diagrams, ductile versus brittle behavior, Hooke's law, E, Poisson's ratio, Nu, shear response, G, and worked examples, tutorials.
Here is our team members: Hanazal, Hafizal, Huzaifa, Hafiz, and Bashir.
The strength of a material is its ability to sustain load without excessive deformation or failure. We determine this experimentally using a tension or compression test to obtain the relationship between average normal stress and average strain. From tension, compression tests, we compute and plot stress, sigma, versus strain, epsilon, to obtain the conventional, engineering, stress-strain diagram. Informal, we turn the raw pull-push data into a curve that tells the whole story of the material's behavior. Definitions. Engineering stress sigma equals P, A. Load divided by original area. Engineering strain epsilon equals delta L, L. Change in length over original gauge length. Likewise, the nominal or engineering strain is found directly from the strain gauge reading or by dividing the change in the specimen's length by the initial gauge length, L0. Here the strain is considered to be constant throughout the region between the gauge points. Thus, epsilon equals delta L, L, using extensometer strain gauge readings, assumes uniform axial strain between gauge points. No two stress-strain curves are exactly identical. Composition, microscopic defects, manufacturing, loading rate, and temperature all matter. Take steel as an example to be discussed. The steel stress-strain curve illustrates key regions: linear elastic behavior, yielding, strain hardening, necking, and fracture. In the elastic region, stress is proportional to strain, linear elasticity. The upper bound of linearity is the proportional limit sigma_place. Slightly beyond, the curve bends to the elastic limit. Unloading here still returns to the original shape. Yielding, start of permanent deformation. Just above the elastic limit, yielding begins. Permanent, plastic, strain accumulates. The stress at yielding is sigma_y. Low carbon or hot rolled steels may show an upper and lower yield point. After yield is reached, elongation can continue at constant load, perfectly plastic region. Strain hardening, climbing to ultimate stress. After yielding, added load raises stress again as the material strain hardens, up to the ultimate tensile stress sigma_u. Necking and fracture, the final stage, figure 3.3. At the ultimate stress, the cross-sectional area begins to decrease in a localized region of the specimen, instead of over its entire length. This phenomenon is caused by slip planes formed within the material, and the actual strains produced are caused by shear stress. True stress strain, why, when to use it. True stress strain use the instantaneous area and length at load application. While the true and engineering curves differ, most design stays in the elastic region where strains are small and engineering values deviate by approximately 0.1%. Hence conventional diagrams are widely used. Conventional diagram details, figure 3.4, mild steel. A typical mild steel curve accentuates the elastic region. In order to enhance the details, the elastics region of the curve has been shown in light blue color to exaggerated strain scale, also shown in light blue. Ductile versus brittle, why it matters. We classify materials by their stress-strain response. Ductile materials yield when maximum shear stress exceeds shear yield. Brittle materials fail when maximum tensile normal stress exceeds ultimate tensile stress. Ductile equals bends a lot before breaking. Brittle equals snaps with little warning. Design rules differ for each. Measuring ductility, percent elongation. Percent elongation equals fracture strain times 100%. If L is original gauge length and L_F is at fracture, percent elongation equals L_F minus L, L, times 100. For the example curve, epsilon underscore f equals 0.380 right pointing arrow 38% elongation. Here A0 is the specimen's original cross-sectional area and AF is the area at fracture. Mild steel has a typical value of 60%. Other metals and the 0.2% offset yield, aluminum, many metals show similar ductile patterns. Constant yielding isn't universal. Aluminum often lacks a clear yield point, so we define yield strength via a 0.2% offset method. Draw a line parallel to the elastic slope at epsilon equals 0.002. Intersection with the curve is sigma underscore yttrium sulfide. Example: sigma underscore ys approximately equals 352 megapascals, Fig. 3.5. Nonlinear elasticity, polymers, rubber. Some materials, e.g., natural rubber, don't have a proportional limit. Stress strain is nonlinear but still elastic. Fig. 3.6. Wood is often moderately ductile and is designed for elastic loading. Properties vary with species, moisture, age, and knots. Tension, compression differ parallel versus perpendicular to grain. Tension is usually intended parallel to grain. Specifically, wood splits easily when it is loaded in tension perpendicular to its grain, and consequently tensile loads are almost always intended to be applied parallel to the grain of wood members. Brittle materials, tension versus compression. Brittle materials, e.g., gray cast iron, show little, no yielding in tension. Fracture initiates at flaws and propagates rapidly. So tensile fracture stress is variable, average is reported. In compression, cracks close and the material carries higher stress. Large strains give barrel-shaped specimens. Here fracture at F equals 152 megapascals took place initially at an imperfection or microscopic crack and then spread rapidly across the specimen, causing complete fracture. As a result of this type of failure, brittle materials do not have a well-defined tensile fracture stress, since the appearance of initial cracks in a specimen is quite random. Instead, the average fracture stress from a set of observed tests is generally reported. A typical failed specimen is shown in Figure 3.8a. A typical full stress strain diagram shows sigma underscore c underscore max greatly exceeding sigma underscore t underscore max, e.g., approximately 34.5 megapascals versus approximately 2.76 megapascals. Hence concrete is almost always reinforced with steel when tensile loads are expected. Fig. 3.9. Temperature and composition effects. Figure 3.10. Most materials can be more brittle at low temperature and more ductile at higher temperature. Steel's behavior also varies with carbon content. Higher carbon right pointing arrow more brittle. Fig. 3.10 shows a temperature-dependent response for a methacrylate plastic. Hooke's law, modulus of elasticity E. Within the linear elastic range, sigma proportional epsilon, so E equals sigma, epsilon. E is the slope of the straight portion of the stress-strain curve. Units of E are pascals. Same as stress, since strain is dimensionless. Steel's E and proportional limit, Figure 3.11, most steels, from mild to tool steel, have similar E approximately equals 200 gigapascals, though proportional limit varies with carbon content. Poisson's ratio new lateral versus longitudinal strain. Under axial tension, a bar elongates, delta L, and contracts laterally, delta R. Longitudinal strain epsilon underscore long equals delta L, L. Lateral strain epsilon underscore lat equals delta R, R. Poisson's ratio nu equals minus epsilon underscore lat, epsilon underscore long, negative sign since axial elongation causes lateral contraction. Poisson's ratio nu lateral versus longitudinal strain. Under axial tension, a bar elongates, delta L, and contracts laterally, delta R. Longitudinal strain epsilon underscore long equals delta L, L. Lateral strain epsilon underscore lat equals delta R, R. Poisson's ratio nu equals minus epsilon underscore lat, epsilon underscore long, negative signs since axial elongation causes lateral contraction. Specific values vary with composition and processing. For ductile materials, yield and ultimate strengths are often taken equal in tension and compression. For wood, properties and deformations are reported relative to grain direction, parallel versus perpendicular. Worked example 1A-36 steel bar, figure 3.13, given. E approximately equals 200 gigapascals. Nu approximately equals 0.29, L equals 1.5 meters. Section 100 times 50 millimeters, A equals 5,000 square millimeters, P equals 80 kilonewtons. Steps. Sigma equals P, A equals 16 megapascals, epsilon equals sigma, E equals 8.0 times 10 to the power of 5. Delta L equals epsilon L equals 0.12 millimeters. Lateral strain equals minus nu epsilon equals minus 2.32 times 10 to the power of 5. Right pointing arrow delta B approximately equals minus 0.00232 millimeters, 100 millimeters width. Delta H approximately equals minus 0.00116 millimeters, 50 millimeters thickness. Informal, it barely stretches, 0.12 millimeters over 1.5 meters. And gets a hair thinner, microns level. In shear, ductile materials show linear elasticity up to a proportional limit, then reach an ultimate shear stress tau_u, followed by loss of shear strength to fracture tau_f. Fig. 3.14. Let's say the example, tau equals g gamma, where g is shear modulus, slope of tau gamma in the elastic region. The elastic constants relate by E equals 2g, 1 plus nu. Given any two, we can compute the third. Informal, shear version of hook. Stress equals stiffness times shear strain. And the E, g, nu are a little family, no 2, get the third. Worked example 2 shear on titanium, figure 3.15, given. Tau_place equals 360 megapascals. Tau_u equals 504 megapascals. Gamma_place equals 0.008 radians. Block H equals 50 millimeters. Base 100 times 75 millimeters. Results. G equals tau_place. Gamma_place equals 45 gigapascals. D_max equals gamma_place H equals 0.40 millimeters. Required shear force at tau_place. V equals tau_place A equals 2.7 mn. Worked example 2 shear on titanium, figure 3.15, given. Tau_place equals 360 megapascals. Tau_u equals 504 megapascals. Gamma_place equals 0.008 radians. Block H equals 50 millimeters. Base 100 times 75 millimeters. Results. G equals tau_place, gamma_place equals 45 gigapascals. D_max equals gamma_place H equals 0.40 millimeters. Required shear force at tau_place. V equals tau_place A equals 2.7 mn. Tutorial 5 Problem 1, Diameter change, given. L equals 100 millimeters, D equals 15 millimeters, P equals 10 kilonewtons, E equals 70 gigapascals, nu equals 0.35. Results. Delta D approximately equals minus 0.00424 millimeters, minus 4.24 micrometers. Tutorial 5 Problem 1, Diameter change, given. L equals 100 millimeters, D equals 15 millimeters, P equals 10 kilonewtons, E equals 70 gigapascals, nu equals 0.35. Results. Delta D approximately equals minus 0.00424 millimeters, minus 4.24 micrometers. Informal, super tiny thinning, microscope territory. Tutorial 5 Problem 4, Permanent shear strain, given. A equals 3 mm at H equals 150 mm. Right pointing arrow gamma underscore total equals 0.02. Tau underscore Y equals 130 megapascals at gamma underscore Y equals 0.005. Right pointing arrow G approximately equals 26 gigapascals. Elastic recovery dg equals tau underscore Y, G equals 0.005. Right pointing arrow gamma underscore perm equals 0.02 minus 0.005 equals 0.015 radians. Closing and acknowledgement. In summary, we've covered experimental foundations for mechanical behavior, conventional and true stress strain definitions, classification into ductile and brittle, and core elastic constants, E, nu, G, with their relationships. Worked examples and tutorials demonstrate practical calculations.